Okay, we're going to continue on here. Chapter 15, wrap it up, and then we will roll into 16. Then we'll roll out of here, hopefully. So really last time we focused in on kind of titrations and solution stoichiometry. And as we talked about last time, really the kind of good news is it's pretty much all the same sort of steps. So we have our basic stoichiometry steps, which again is our balance, our equation, our convert to moles. Remember always when you're doing any stoichiometry problem, solution, gas, regular stoichiometry problem, you always want to double check to make sure that's not a limiting reagent type situation. If it is, obviously you do need to solve for it. If it's not, then you don't have to worry about it. Three, we want to do our actual stoichiometry or mole to mole relationship. And lastly, here we want to go from moles to some other unit. As we talked about last time, the main sort of difference when we do solution stoichiometry is really we incorporate molarity along the way. So molarity again is our moles per liter, and I would say early on in the calculation, if you're going to use it, which is very common as step number 2, you're going to use it to solve for moles. And as we've talked about a number of times, you do want to always make sure that you are in liters when you're using it with molarity. That way you'll get moles, which is again probably what you're looking for. Again, you do not want to use milliliters with molarity, otherwise you will get probably the wrong unit that you're looking for. The other very commonplace, especially in titration problems and solution stoichiometry problems, is we use molarity here on the back end, and we would use the stoichiometry to get the moles, and we could solve for molarity. Taking the moles from the stoichiometry, the volume would most likely be given to you in that case. The other very common one, like we did as well, I think last time, is to solve for a volume, which is moles divided by molarity. Once again, in each of these cases, the moles are coming from the stoichiometry part of the calculation. Either the molarity or the volume would be given to you in that situation. Any questions on that there? All right, so I want to try another one here, just to make sure. If a titration requires 63.5 milliliters of 0.375 molar calcium hydroxide to reach the equivalence point in a titration of 95.5 milliliters of hydrobromic acid, what is the molarity of the hydrobromic acid? So I want you to take a few minutes or so and go through those steps and see what you end up with here. Stoichiometry. So we do need to start with the equation. So we want to start first off with the right formulas, and then we want to balance. So calcium is +1, hydroxide is -1. So that's going to give us not a 2 there. That's going to give us a CaOH2 on the bottom. Hydrobromic acid is HBr. Remember that when you take an acid and a base, you pretty much get water for sure there. And in most cases, you'll get our H2O. And remember, our salt is going to come from really the other guys coming together here, which again, we want to put together properly. So calcium is +2, Br is -1, which gives us CaBr2 in this case. Remember, we want to get the right formulas first before we even think about the balancing aspect of it. Here we do need to balance it, and if we balance it, I think we need a 2 there and a 2 there. So now we have our balanced equation, which, as we've talked about many times, it doesn't work if you don't have that balanced equation, right? Any questions on how to get the equation there? Really a double displacement reaction is sort of happening in this case. Now that we have the balanced equation, we want to think about what was given to us. So think about what we need to solve for. We're given 63.5 milliliters of our calcium hydroxide. We know the molarity here, 0.375 m. Over here for our HBr, we're given a volume, and we are looking for the molarity. So first off, obviously it's non-limiting reagent type situation. Since we're looking for something about our other reactant, it's just a basic stoichiometry problem. And really this guy on the left here It's the only one we could really get to moles to begin with. Now, if we think about the molarity of our HBr in this case, moles per liter, we already really have the liters part of it. We just need to do the conversion. So again, really, we're going to use the stoichiometry here to figure out the moles part of the HBr so that we can then calculate the molarity of it. So to do that, remember, we do need to convert our volume here into liters. So that's going to be 63.5 milliliters. 1,000 milliliters in a liter. Going to get us 0.0635 liters of calcium hydroxide. Also, remember that our molarity here, we don't want to use it as a big M. So we want to use it more like a conversion factor. So 0.375 moles per liter. And that's actually the way that we do want to use it. So the liters cancel. So that is what we will do next. We'll take the molarity of the base in this case. The liters here will cancel, and that's going to get us, call it 0.02381. Remember, though, that these are moles of calcium hydroxide. We need to get ourselves over to HBr, and that is where the stoichiometry now comes into play, right? So our mole to mole relationship from the equation, and we can see in this equation for every 1 mole of calcium hydroxide, we get 2 moles of HBr. So that will be our next step here. And we want the HBr up on top, so we are left with it. We want the calcium hydroxide to cancel out. Moles will cancel. Gonna get us here then 0.04763. And now that we have that, that really is the top part of what we need. So we now have really the top and the bottom. We still need to do a little conversion there on the volume there for our hydrobromic acid. So we'll do that. 95.5 milliliters, same 1,000 milliliters in a liter. Going to give us 0.0955 liters. We now have the moles. We now have the volume in the correct units. All that's left is to do a little division. So we're going to take 0.04763 moles divided by 0.0955 liters. That's going to get us here 0.499. And again, you can leave it one of both ways. You can leave it as moles per liter of HBr, or actually go to the left of it there. You could write 0.499 big M HBr. So either way is fine in that case. Any questions on those steps there? Again, it is still our same 4 steps we've been doing for a long time at this point. Balancing the equation, converting to moles, mole to mole relationship, and moles to some other unit. So still the same 4 sort of steps, just incorporating our molarity here in 2 spots in this case. Any questions on that there? So a reminder that you do need to write the equation when you have a stoichiometry problem. You do need to work it out like that. You should not use something, which is a very common mistake a lot of people will use, like the dilution equation, M1V1 equals M2V2. That really should only be used for dilutions and not titrations like this, especially if you like all the points. You do need to show all the work with the equation, stuff like that. Sometimes people look it up or are taught they could use that for titrations, and it does work for only specific type of titrations where you have a mole-to-mole relationship of 1-to-1. And in this case, obviously, it's not a 1-to-1 relationship, which means you will not get the right answer because you will not have the right stoichiometry involved. So if it's stoichiometry, titration, solution stoichiometries, I highly recommend you show it this way if you like all the points, and do not use the dilution equation in a situation like this. Any questions on that there? Questions on stoichiometry? Okay. So to finish up this chapter here, we're just going to briefly talk about another sort of unit that, I don't know, nowadays really doesn't pop up all that much. Maybe in 1A they might make you do something like that, but normality is another unit of concentration, and normality is actually kind of like molarity, and it is, and sometimes you might even see it on a lot of manufacturers when they send out reagents. They give the molarity, or I guess concentration and normality. Like for example, when you did your titrations, that big box of base, or even the acid, are sometimes sent in terms of normality. Normality, as we will see in a second, has units of equivalents per liter. And what is an equivalent? Well, an equivalent in the case of an acid or base really depends on how many H pluses an acid has the ability to sort of give away. And for a base, it's how many hydroxides, for example, that a base will sort of give away or sort of lose in solution. So if we have a monoprotic acid, which means it has one hydrogen to give, something like HCl. When that breaks apart in solution, you get an H plus and a Cl minus. It gives away basically one H plus, which means we really use equivalents a lot of times as like a conversion factor. We can say for every 1 mole of HCl, we get one equivalent, and that's because it only gives away one H plus. If you had something like a diprotic acid, which gives away two hydrogens, something like H2SO4 will overall give away two hydrogens and have a little sulfate action happening. So for something like that, we could say for every 1 mole of H2SO4, we get two equivalents, and something like a triprotic would give you three equivalents. We could also do this, like I said, for bases as well. So like sodium hydroxide would give you a sodium and one hydroxide, which means 1 mole of sodium hydroxide would give you one equivalent of hydroxide, basically. And like the base that we just looked at there in that problem, 1 mole calcium hydroxide would give you two equivalents because it would break apart into two hydroxides that we saw there. So normality is something that we use sometimes to calculate equivalence, sometimes equivalent weight, or sometimes it's referred to as equivalent mass. Is kind of like the molar mass in a sense, but using equivalents instead of grams per mole. And to calculate that, equivalent mass is basically grams per equivalence instead of, again, grams per mole in this particular case. As we will see in certain cases, the equivalent mass and the molar mass will be the same. And same thing with the molarity and the normality will be the same in certain cases. In some cases, they will be different. Any questions on that there? So some strong acids and bases that we've talked about previously. Again, a reminder, we could add a few to our list here: perchloric acid, hydrobromic acid, hydroiodic acid. Remember, things in group 1 and group 2 are a lot of the strong bases like calcium hydroxide, strontium hydroxide, barium hydroxide, lithium hydroxide. So a lot of those guys in group 1 and group 2, lithium, sodium, potassium, hang right, calcium, and down are strong bases. And again, these guys, because they're going to 100% break apart in solution, will produce a certain number of H pluses or OH minuses that you could use for equivalent mass or normality. So let's take a look at one here together just to sort of talk about how we go from, say, one to the other. So let's say we wanted the equivalent mass or equivalent weight here of this acid, arsenic acid. One way we would start is to go from molar mass, which is grams per mole, to equivalent weight or mass, which is grams per equivalent. And really the top part doesn't change, but it's just the bottom part that needs to change. So to do that, we would get the molar mass here of our acid from the periodic table like normal. We would take 3 times 1.008 for our hydrogens, plus our arsenic, which is like 7492, I think. And our 4 oxygens. And if we do that there, called 141.9. And at this point, like I said, we really just need to do that relationship and that conversion. And because this is actually a triprotic acid in this case, it's going to break apart into 3 hydrogens eventually and ASO4 3 minus. And here we would use that to give us our conversion factor, and 1 mole of the acid, because it could give 3 hydrogens, will give us 3 equivalents. That means all we have to do is a little conversion here, and we will do moles up on top so they cancel. 3 equivalents. And here we end up with 141.9 divided by 3 gives us 47.3. I think. Equivalents, grams per equivalence here. So the molar mass of this acid and its equivalent mass is a third, because of the number of hydrogens that there are in this particular solution. Any questions on that there? So if we took something, for example, like HCl and got the molar mass, which would be 1.008 for our hydrogen, plus 3545 grams per mole, will get us there 46 46 grams per mole. But because hydrogen is monoprotic, for every 1 mole of HCl, we will get 1 equivalent because it only has 1 hydrogen to give. That means if we convert this into equivalent mass, we will have a mole is 1 equivalent. They cancel, and we end up with 3646 grams per equivalent. The molar mass in this case and the equivalent mass will be the same, because it only has basically 1 hydrogen to give, or 1 equivalent. So if it's really monoprotic, or a base that has only 1 hydroxide to give, the molar mass and the equivalent mass will pretty much be the same number, because you're just multiplying by 1 basically. Any questions in that case, or dividing by 1? So as I mentioned before, normality again is another common unit. And again, it is equivalents per liter. So a lot of times what you would be doing in this case is, perhaps if you had the molarity, which is our moles per liter, you could take it to the normality, which is equivalents per liter, by using our same sort of conversion to convert really the top part of it there, to go from molarity to normality, or vice versa if you need to go obviously the other way as well. So if we needed to do that here, if we take a look at 2.5 molar sulfuric acid, we want to know the normality. Once again, that is 2.5 moles per liter of H2SO4. We basically want to get it to equivalents per liter. As I mentioned a second ago, this stays the same. So we're going to use our relationship to do that. And we can see for every 1 mole of H2SO4, We should get two equivalents because again, H2SO4 will basically generate two hydrogens. So again, that is basically where the equivalence part of it comes from. So we'll use that as a conversion, 2.5 moles of H2SO4 divided by liter. And in this case here, two equivalents per mole of H2SO4. In this case, we're actually going to multiply by 2. And it would be 5 equivalents per liter. Or you could write it kind of like you do with molarity, 5 big N H2SO4. So kind of similar to how you deal with molarity, write that big M. You could also write the big N here in this case, and that will give you your normality. So in this case, because of the two hydrogens, the concentration, our normality is actually twice the concentration here of the molarity in this case. Just like with our HCl, if we had 2.5 molar HCl, when we would get down to it, because as we saw in the previous one, HCl is a 1-to-1 relationship, we would have 1 mole of HCl, 1 equivalent of HCl. And that means that our molality here will be 2.5 N for HCl, which matches the molarity. So again, if something's monoprotic, basically has 1 hydrogen or 1 hydroxide, both the molality and the normality will be the same. If it gives more than 1, then your normality and molarity will be different. And same thing with equivalent mass versus molar mass will be the same if it's a monoprotic versus it will be different if it's di or triprotic. Question on normality. Although we don't use it too much these days, it may pop up maybe in 1A. They used to years ago do like a titration experiment where you calculate the equivalent mass of your unknown acid and stuff like that. So still pops up occasionally. You could use normality because it is a concentration in any type of concentration type of situation. So you could do a dilution with normality. You could do stoichiometry if you wanted to as well with normality. So you could kind of do the same kind of things you could do towards calculation with molarity as you can do with normality as well. Any questions on any of that there? All right, that's going to wrap up, I think, here chapter 15. We're going to go to chapter 16 next. Okay, so chapter 16 here is we're going to talk about acids and bases in this chapter and talk about what acids and bases are, some relationships that occur with acids and bases. We'll talk about obviously acidic, basic, neutral solutions, how to calculate pH, and we will finish up with buffers hopefully. So let's get into it. So acids and bases, acids were first recognized by their sour taste. We come across acids a lot, like you used last week. Acetic acid, which is the major acid there in vinegar, or citric acid, for example, in lemons. Bases are characterized by bitter taste. They have a slippery feel. A lot of soaps, drain cleaner, and stuff like that are pretty much strong bases. They're also sometimes referred to as being alkaline, for example. Bases, alkaline means basic, pretty much. And if you think about where we find our strong bases on the periodic table, that's group 1 and group 2, which is our alkali metals and our alkaline earth metals. And again, that is really where we get a lot of our strong bases from. They do change litmus paper, by the way, colors. Litmus paper is paper that you could dip your solution on. And if your litmus paper typically turns red, that means it's acidic. And if your litmus paper turns blue, that usually means that that solution is basic. So sometimes in the lab, we use litmus paper a lot to determine whether or not something's acidic, basic. I guess you could also use a neutral as well. They have neutral litmus paper as well, but usually acidic or basic. Now, sort of an early definition of acids and bases was one done by Arrhenius here. He did a lot of work with electrolytes. If you remember, electrolytes are things that basically will dissolve in solution and produce ions and be able to conduct electricity. Acids and bases can be strong electrolytes, which again means that they can 100% break apart in solution. They also can be weak electrolytes, which means they will mainly stay together but break apart a little bit. And he defined an acid as something that's able to produce hydrogen ions in solution. And when we talk about something being an acid, we're really talking about the ability of that sort of solution to basically produce H plus ions in solution. And again, these are free H plus ions floating around, not attached to anything. That is basically your definition of an acid. Now, in acid-base chemistry, the H plus ion here is sometimes referred to as the hydrogen ion. It is also sometimes referred to as a proton. And that is because hydrogen has one electron, one proton, and no neutrons, which means when it's positively charged, it loses an electron, which means the only thing left is a proton, which is why it's sometimes referred to that. And if that's not enough confusion, H3O plus, which is known as the hydronium ion, is essentially the same thing as H plus in terms of acid chemistry. So H plus, H3O plus can be interchanged both in equations, formulas. I personally will use H plus most of the time, but books nowadays will kind of usually use H3O plus a lot. So anywhere in an equation or a formula I put H plus, you pretty much could just swap it out for H3O plus. And it's really the same thing. It means, again, the acidic part of the solution. And the reason, for example, why you might versus H3O plus is really what you include in your equation when you write it. So for example, if we took something like hydrochloric acid, which is a strong acid, and we just want to describe how it's going to fall apart in solution, we could write this equation where it's H plus and Cl minus, right? And that really describes sort of what happens when you put something like HCl, in water or in solution. It's just going to fall apart. It's going to produce a lot of H plus really quickly, by the way, which is why it's a strong acid. It's going to produce a bunch of H plus by just going for a swim. You can just as properly, I guess is the way to say it, write this equation where you actually do put the water into the equation. And if you put the water into the equation to show that what is happening is really the HCl is going to send the H plus over actually, and you will make H3O plus in that case and Cl minus. And again, for all intents purposes, they are the same, the H plus or the H3O plus. So sometimes people describe it as a free H plus in solution. Again, it also means essentially that H plus is going to find some water really and make H3O plus. So again, it is the same thing. That's the same thing. When we talk about a base, he defined a base as something that has the ability to produce hydroxide ions in solution. And it's sort of the same idea. When you have a base, what we're looking floating OH minus is again not attached to anything, just kind of floating around. And again, if you took something like sodium hydroxide, it will do that. It will 100% break apart into sodium ions and hydroxide ions. And that is why sodium hydroxide, for example, is a strong base, because as soon as that goes for a swim, you're pretty much producing a bunch of free hydroxide really, really quickly. And it's going to increase the amount of hydroxide in that solution and probably in a lot of cases make it basic if it was added to something like water for sure. Any questions on that there? So this definition of an acid and base was a really good one. And again, this is basically how we get both of those things. You could take hydrogen chloride gas and dissolve it in water, and you'll get the aqueous ions that are floating around. We talked about in a previous chapter how to name acids, right? And it involves whether or not it has oxygen or not, right? As to sort of whether you use hydro or you don't use hydro in terms of naming it. But also really important, as we talked about, was when you write formulas for acids, you do include the aqueous ion next to it, or the aqueous symbol. And that implies that it's an acid, and that's hydrochloric acid, where it would be hydrogen chloride gas. Also, acid, the H plus is always the positive ion when you have an acid. And again, there we have our sodium hydroxide dissolved in water will definitely produce that. And in each of these cases, we're going to get a bunch of H pluses. Also, we'll have some Cl minuses, which will not affect really anything in terms of the that strong acid. Same idea here. We will have a bunch of sodium ions, which is not important for the H or anything like that. But those free hydroxide, cases sodium hydroxide, are really important for whether or not, again, that solution may be acidic, basic, or neutral. And that's really how we determine sort of if a solution is acidic, basic, or neutral. It's basically the ratio of how much H plus you have floating around freely in that solution to how much OH minus you have freely floating around basically in that solution. Now, it was a really good sort of step in terms of acid-base chemistry, but he did a lot of work with bases that actually had hydroxide sort of on board or in the formula. And not all bases will have hydroxide actually in their formula. So, for example, something like ammonia, which is NH3, that is actually a weak base, which means when it reacts or goes for a little swim there with water, it's actually going to accept an H plus from water. And the result of that is you will make NH4 plus, which is ammonium, and you will make hydroxide. So here it is able to produce hydroxide, which is why it's still considered a base. But you might remember these arrows that head in both directions. We see that with weak electrolytes. We have our forward direction going from reactants to products. We have our reverse direction going from products back to reactants. And if you remember, something that's a weak electrolyte is going to mainly stay together, which means it's only going to produce a little bit of hydroxide, and it would not be able to produce anywhere near, for example, the amount of hydroxide. So if you had this, you would have a lot of NH3 still in there. You'll have some NH4 plus, and you'll have a little bit of OH minus kind of in there as well. But that's nowhere near what, again, will happen when we take a strong base like sodium hydroxide, whereas I drew in the previous slide there. When that's going in, we're going to get a lot of sodium, but more importantly, we're going to generate a lot more hydroxide than you would versus ammonia. Because all sodium hydroxide, for example, has to do is go in and it's going to break apart. Ammonia's got to go find some water, do a little bit of reaction, and produce a little bit of hydroxide. So it's not going to be able to produce as much hydroxide as efficiently as sodium hydroxide would be able to do. So although they both are able to produce hydroxide, that is why they're both considered bases, but that's why I'm considered a hydroxide. Questions on that there? So the next really big definition of an acid and a base is one that's known as the Bronsted Lowry definition of an acid and a base. And a Bronsted Lowry acid, something that will donate a proton, and a base is something that will accept a proton. When we talk about the proton, which is the H plus, it is really important to remember the plus part of it. And I would say most people forget about the plus part or not sure what to do with the plus part of it. So although somebody may be accepting an H or donating an H, they're also accepting or donating the charge, if you will. So if somebody loses something that is positively charged, like a proton. You then have more electrons than protons, so you become one more negative. If somebody gains a proton, they then gained a positive guy, which means their charge should change to one more positive. So it's really important when you sort of do these reactions that you realize that the charge actually changes. What do I mean by that? For example, we take a couple of those reactions that we just saw. We take our HCl plus our water. And in this case, this is an acid, and water is going to act as a base in this case. And the HCl is going to send the H plus over. When it does so, the water gains the H, and it was neutral, but also gains the plus, so it becomes H3O plus. So this charge changes. The HCl loses an H and was neutral to start with, which means the Cl becomes one more negative. And that is what happens. We get those charges to change. By the way, there is a relationship between the left-hand side of the arrow here and the right-hand side of the arrow. The acid on the left is related to this guy on the right, which is known as the conjugate base. And the base on the left is related to the guy on the right here, and that is known as the conjugate acid. The only difference between the acid and its conjugate base and the base and its conjugate acid is this one little guy right here. That one H plus is the only difference that there can be. So as you go from the acid to the conjugate base, it has one less H plus. As you go from the base to the conjugate acid, it has one more H plus as it accepted it. By the way, we can also see that in the other equation that we looked at, NH3 plus our water. And in this particular case, it is the NH3 that's going to accept the H plus, and the water is going to send it over. That means that the water and the NH3 between those two is that H plus that has been transferred. Once again, we see the NH3 gains the H plus, so it goes from neutral to positive on the other side. We see the water, which was neutral, go to basically negative on the other side as it loses the H plus. These are the consequence of the Bronsted Lowry definition is you actually create partners on opposite sides of the arrow, and the partners are related to each other by that one H plus only for them to be partners. We also see here something that does happen as well, and that is if we look at our friend water, in this case it was an acid, and in this case water was a base, and there are certain substances that can act as an acid or a base, and that's known as being amphoteric. Can act as an acid or a base, and water is an example of that. It's actually what happens when water's with water. One water is an acid, one water is a base, and that's constantly what's sort of happening in your beaker of water that you have going on in that case, and we'll talk a little bit about that in just a bit. But things can definitely sort of go both ways if they have the hydrogen to give and if they can accept the. Any questions? And I think I said so that's what we see here. HA is just a generic sort of for an acid. And again, in this situation, water creating our pair, our other pair. is getting transferred is the only difference that there can be. All right. And there's our HCl example we just talked about. And this again is what's typically happening here. That H bond between the HCl and hydrochloric acid is the one that's coming off, and it's going to go find a water that's floating around and produce that H3O plus. Typically speaking, if you ever look at an equation and you see on the right-hand side of the equation H3O plus or H plus, probably an acid type situation occurring. If you see on the right-hand side of the arrow OH minus by itself, probably a basic type situation that's occurring if you have some type of equation. Obviously, our hydronium ion, our H3O plus here. Second ago, same. Why don't you take a moment for each of these to determine whether or not these guys are conjugate acid base pairs. So again, looking for a difference. Okay, so let's take a look. So again, really what you're looking for is 1H plus and 1H plus difference in order for these to be pairs. So if we look at the first one, we have HClO4, ClO4 minus. So really the only difference here is 1H plus. You could either take off the first one, you get the second one, or put it on the second one, you get the first one, right? So this would be a pair. We look at the second one here, HCl, ClO minus. The difference here is 1H plus. It also is a difference of an oxygen, right? So this one has an oxygen. This one obviously does not, which means even though it's still an H plus difference, it is not a pair. It could only be, for them to be a pair, only one H plus basically difference. So if we look at the next one here, H2PO4 minus, HPO4 2 minus, relationship here is 1H plus, and that would be a pair. By the way, this is also talked about in terms of the charge changes. So for example, when this guy loses his H plus, it has a hydrogen, a phosphorus, and 4 oxygens. It loses a positive, becomes one more negative, which is how it gets to -2 over here. So again, very common. People sort of forget about the plus part of that and just do the hydrogen part. So you want to make sure you adjust the charge accordingly. Difference between these two is also 1H plus, which means that guy should be a pair as well. Any questions on any of those there? Is H2SO4 and SO4 2 minus, are they pair? The answer is no, they are not a pair. Difference there is not 1H plus, but it's actually 2 H pluses. Yeah. And again, it can only be 1 H plus. Something like sulfuric acid is a diprotic acid, which I mentioned earlier, has 2 hydrogens that come off. By the way, the hydrogens don't all pop off at once. They actually come off in a stepwise fashion. So what actually happens is the sulfuric acid will lose 1 hydrogen and make HSO4 minus. And it's that HSO4 minus that will then lose its second hydrogen and make sulfate. And it actually is was referred to as a stepwise dissociation, happens in steps. Do you think it's easier to get off the first hydrogen or the second one? Which one should be easier? It's actually much easier to remove the first one. It's neutral, right? After you pop off it, the first one, you now have something that's negatively charged, and you're starting to remove something that's positively charged, right? So it's going to be held a lot tighter. In fact, most of the hydrogen comes off in the first one, very little comes off in the second. If you have something like phosphoric acid, it has 3 hydrogens. By the time you get to the third hydrogen, barely any of that comes off. A majority of all of it comes off in the first part. That is why, though, if we are looking for pairs for these guys, this guy here and this guy here, those are pairs. The only difference is 1 hydrogen. H plus. This guy here and this guy here are also pairs because the only difference is one hydrogen. And as we saw on the bottom, going directly though from there to there is a two-step process, and they are not going to be pairs in that particular case, kind of going through both of those in that case. Any questions on that there? All right, so I want to try with some here. For each of these, why don't you write what the formula of the conjugate base would be if you start. Okay, so let's take a look. And again, in this case, we're looking for the conjugate base for each of these things. And this is where understanding the relationship that we talked about earlier, that you have the acid and the base on the left-hand side, and you have your conjugate acid and your conjugate base on the other side. Acid and conjugate base related, base and conjugate acid. So when you have a question like this, if they don't really tell you what it is, or you're not sure what it is, you know you want to end up at the conjugate base, which means if you follow it backwards, everything you're staring at here is basically an acid. And all you have to do is use the Bronsted Lowry definition of an acid, which is it should donate the H plus. So hopefully you know it should be an H plus, but most people struggle with should you put it on or take it off. So if you think about it sort of backwards here, and we know that these are acids, all we have to do is take it off. So we're just going to remove an H plus for each of these. That will leave us an H and an S. And once again, it was neutral. Because of the plus, it will now become negative, which is important here. Make sure you got that charge. That HS minus will now leave us with just an S, and it was -1 to begin with. So lost another positive, becomes -2 in this case. So S2 minus. Here we're going to take off a hydrogen, which will leave us two hydrogens. Was neutral, now it should become one more negative. And lastly, here we'll take off one of these hydrogens, which will leave us HSO3 and a minus in this case. Any questions on any of those? Now, as we talked about earlier, there are certain things that can be amphoteric like water, but a lot of times if you have something with a hydrogen and a negative charge, it oftentimes can go both ways because it has the hydrogen to give. It also can accept the hydrogen. So let's just say we started with bicarbonate here. Why don't you write the conjugate base for it? Why don't you also write the conjugate acid? Again, in each case, starting with bicarbonate. Okay, let's take a look. So in the case, we'll start with conjugate acid. So if we're starting with that guy and we want conjugate acid, if we go backwards, in this case, it's going to act as a base, which H plus, putting on the H plus here, and that would give us H2CO3 when it's all said and done. If we look at the conjugate base, like we did in this question, that means just like in this question, we're looking at it as an acid, which means it's going to actually donate the H plus, and that will leave us CO3 become one more negative, and we'll be left with carbonate in this case. Any questions on either of those? Sometimes it's good to think about backwards because very common, they will not tell you what they are if they're acids or bases. They will just ask you to write the formula for the conjugate acid or conjugate base. So again, if you just sort of think about it backwards, follow the Bronsted Lowry definition of an acid and base, you should be able to hopefully figure it out. Any questions on conjugate acid base pairs? So talk a little bit about acid strength. We sort of touched upon it. Obviously, we have two types of acids. We have strong acids, which again, 100% break apart in water. And we do have those kind of weak acids, which again will go in both directions, mainly stay together, but will be able to again produce a little bit of H3O plus. And as I mentioned earlier, because they both have the ability to still produce H plus or H3O plus, they're both considered acids. But once again, in comparison, a strong acid is definitely going to be much, much stronger than any weak acid because a strong acid just needs to go in to the beaker, for example, and it will produce a lot of H plus really, really quickly. So if the forward direction predominates, we do have our strong acid, which again is going to 100% ionize or completely dissociate. Those are fancy words to say it completely breaks apart into ions, basically. And that would obviously be something like we've been talking about, like our hydrochloric acid. And once again, in a solution of hydrochloric acid, that is pretty much all you have in there are your ions. And in this case, a lot of H pluses. And that's different than, say, something like hydrofluoric acid, which is a weak acid. Hydrofluoric acid will still break apart into H plus and F minus. But in solution, that is, again, mainly what you have. You have a little bit of these guys. So if you looked at a beaker of that, you're going to find yourself with a lot of HF in that solution and a little bit of H plus and F minus. So since it's still able to produce some H plus, still consider an acid, but like I mentioned before, nowhere near as strong of an acid as those strong acids that we talked about, which again is our hydrochloric acid, our nitric acid, our sulfuric acid, and our other ones that we added to our list. Again, hydrobromic acid, hydriodic acid. Now, in terms of a relationship, which it's good to know, but really when you get to 1B, you'll definitely need to know this relationship for sure. And that is the relationship between, say, an acid and its conjugate base, or a base and its conjugate acid. And there's really sort of an opposite relationship. So what I mean by that is if you have a strong either acid or base, its conjugate partner will be relatively weak. So its conjugate base or conjugate acid will be relatively weak. What that essentially means is it's not going to affect the pH of the solution. It's just going to kind of hang there and not do much. So it's not going to continue to react or anything like that. It's sometimes referred to as being like neutral. So it's like a neutral sort of salt is sort of the relationship there. Now, opposite of that is if you have a weak acid or base, its conjugate partner is going to be relatively strong. So the conjugate base or the conjugate acid will be relatively strong. So what do we mean by relatively strong? It is not as strong as an acid or base, a regular strong acid or base. What we mean by that is, frankly, if you had something like hydrofluoric acid that we just looked at, where it will break apart into H plus and F minus, that F minus is going to be relatively strong conjugate base. And what that means is it has the ability to continue to react. And what will happen in that case is the F minus, because this is an aqueous solution, there's water in there, will find a water and it will actually continue to react. And the result of that is it will actually make some more hydrofluoric acid, and it will actually accept an H plus and will make hydroxide. So the presence of that F minus, for example, in that solution, say you had a solution of sodium fluoride, which is basically F minus. You would expect that solution to be basic because it will go through this reaction with water and actually continue to react and produce hydroxide. This reaction is what is referred to sometimes as a hydrolysis reaction. Hydrolysis because it involves a reaction of something with water. It's a whole chapter in 1B on hydrolysis reactions. But that's what we mean here by strong. F minus is way weaker than sodium hydroxide, is not as strong of a base or anything like that, but is strong in the sense that it has the ability to continue to react. And because of that, it has the ability to affect the pH of that solution and make it more basic because it's going to be able to produce hydroxide. As opposed to something up here, if you took something like HCl, which is a strong acid, as we talked about, H plus and Cl minus. And this would be our strong acid. This would be our conjugate base. And what happens when Cl minus gets in there with water that's floating around? It has no interest in reacting. and that's why it's considered neutral. It's just going to float around and have a good time. It's not going to continue to react with water, unlike F minus, which is from a weak acid, which means it does want to kind of continue to react. So sometimes when you have these sort of opposite relationships, you can produce something that can continue to react with water. And since acids are aqueous solutions, water's in there, it can continue to react and affect the acidity of the solution. Any questions on that? All right, so we talked about diprotic acids and triprotic acids. And once again, triprotic acid, something, for example, like phosphoric acid, has 3 hydrogens that would come off, and that's known as being triprotic, has 3 hydrogens. Sulfuric acid is diprotic, has 1 hydrogen come off, and HCl, for example, is monoprotic, again, has 1 hydrogen that will come off. So oxyacids, as we might have talked about when we were doing naming, are acids that contain oxygen. And I think we drew this guy one time along the way when we were doing some Lewis structures, I think. That's nitric acid. It's an oxyacid. It contains a polyatomic ion. By the way, it is always this kind of polar OH bond here. That is the hydrogen we're talking about that's coming off. So that is the hydrogen that's actually being broken at that bond, and that is the one that is being released. There's also some organic acids, which are very commonly used, like you used last week, like acetic acid, which looks like this. It has a carboxylic acid group, which is an organic group, also containing that OH bond. That is the carboxylic acid group, that carbon oxygen double bonded to the OH. Once again, here it is still this bond right here that gets broken, and that is still the hydrogen that comes off to make it an acid. By the way, none of those hydrogens over here are going to do anything in this case because they're all nonpolar, so they're not going to break off or anything like that. It's going to be that polar OH hydrogen that's going to really come off to make it an acid. Any questions on that there? So earlier we talked about something being amphoteric, and we saw that water is definitely amphoteric. And as I mentioned, it can react with other waters. And again, one acting as an acid, one acting as a base. And that is what is sometimes referred to as the autoionization of water. And those are our 2 examples where we saw it happening, our NH3 with our water here accepting the H plus, and our water accepting the H plus in the second case, acting as a base. Now, when water reacts with other water, we basically produce H2O, and we make H plus or H3O plus. Again, same thing here, these 2 guys, and OH minus. This is what is referred to as an equilibrium that it will set up. And it will set up what is referred to as the equilibrium constant, which is capital K. And there is a nice relationship that you can use this reaction for to calculate, for example, how much H plus is in the solution, how much OH minus is in the solution. And that is what is known as Kw. And Kw is the ion product constant for water. This is one of the first formulas that we were talking about where you could substitute out the H3O plus for H plus. Concentration of H plus times the concentration of OH minus. It does change with temperature, but for your purposes here, you pretty much can assume that it's a constant of 1 times 10 to the minus 14. Very rarely is it any other number that's used here for Kw. And again, that is the exact same thing as it's written up here of H3O plus and OH minus equals 1 times 10 to the minus 14. Again, H plus H3O plus is basically the acid part of the solution. OH minus is the basic part of the solution. When we have these brackets, that means concentration. And typically we are talking about molarity, which is moles per liter is basically what we're talking about here. So there's a really important sort of relationship that happens between H plus and OH minus, which is an opposite relationship. So as the concentration of H plus increases, the concentration of OH minus decreases. So as one goes up, the other goes down, and obviously vice versa as well. H plus goes down, OH minus is going to go up. We could use the amount of H plus or OH minus in a solution to determine whether or not that solution is going to be acidic, basic, or neutral. If we have more of the H plus, which is the acid part of the solution, then we do the OH minus, then we would expect it to be acidic. If we have more of the OH minus concentration, which is the basic part of the solution, then we do the H plus concentration. We would expect it to be basic. And if they happen to equal each other, that means that they both will have a value of 1 times 10 to the minus 7. And it will be neutral in that case. And that is basically what neutral means. Equal concentrations of both of those things, which should give actually a neutral pH of 7, as we'll talk about. We could use that KW expression, and that is what these are. This is sort of the KW expression we just looked at. And the nice thing is really the same calculation, regardless of which one you are doing, whichever concentration they give you, either the OH minus or the H plus. You basically take 1 times 10 to the minus 14 and divide it by the other concentration. This is a good reminder of 100% in this chapter. Make sure you are definitely using your exponent buttons, or you're going to find yourself way off. I won't say way off, but you're going to find yourself off definitely in this chapter as we do these calculations. So make sure you're definitely using your exponent buttons when you punch these things in. Any questions on that there? All right, so let's take a look at one just to try one here. Take a moment here, make sure you know how to punch it into your calculator. What is the OH minus concentration in this case? We'll just do this first one. And is it acidic, basic, or neutral? So let's take a look. Again, this is a KW situation where we have the H plus concentration times the OH minus concentration. Again, that's also H3O plus. Equals our 1 times 10 to the minus 14. In this case, we're looking for the OH minus concentration, which will be 1 times 10 to the minus 14 divided by our H plus concentration, which would be 1 times 10 to the minus 14 divided by 3.4 times 10 to the minus 4. Once again, a reminder how you should punch this in, perhaps a 1, an exponent button, a negative button, and a 14 divided by 3.4, exponent button, negative button, and 4, and hit equals. And you should get something like 2.9 times 10 to the minus 11. You do need molarity as it is a concentration, and that would equal our OH minus concentration in this case. Any questions on that calculation? At this point, once you have the OH minus, which is like the basic part of the solution, you want to take it and compare it to the H plus concentration, which is the acid part of the solution. In this case, which one is larger, H plus or OH minus? Which one? It is the H plus that's larger. So also a reminder that when you have a negative exponent, that is important, the negative part of that, because that means I'm going 11 places that way and putting zeros, which makes it a much smaller number than only going 4 places that way and putting zeros. So when you're comparing negative exponent, which is again a very common mistake, the smaller negative exponent is the larger number, right? So just keep that in mind. That would mean that again, this guy would be acidic, as the H plus concentration is larger than the OH minus concentration. Any questions on that there?